kind of janky, low key, but like it's fine. I'm kind of bored, so I'm gonna do some stuff with the Schrödinger equation, which I'm sure everybody loves, and it's gonna be great. Definitely. I don't really know what to say. I guess I'm just gonna start a chart out. Schrödinger equation. Essentially, what I'm gonna do here is I'm gonna use the Schrödinger equation, and I'm gonna derive from the Schrödinger equation the equation for, or the non-relativistic equation for the energy of a particle that doesn't have mass, or no, does have mass. My mistake. And I'm just going to show you how to get that, and I'm going to explain some stuff around that, and I'm also going to explain the difference between relativistic and non-relativistic equations, do some stuff with that. So first things first, I'm going to write down what the Schrödinger equation actually is. I'm going to use blue for this, and I'm going to use red for derivatives. Gavin, go away. One of you two, get out of here. So yeah, I'm gonna do that. All right, so Schrödinger equation is gonna start out. Start out with imaginary number I, reduced Planck constant, derivative with respect to t of wave function x of t, which is gonna equal, got Hamiltonian operator, and then it's the same function, right? Yeah, Hamiltonian operator, and then psi x of t. And this is Schrödinger equation, or at least the time-dependent Schrödinger equation. So first thing we'll do is we're going to take the Hamiltonian operator, and we're going to split that up into what it actually is. The Hamiltonian operator is essentially function tx of t v x of t. And these two functions, we have the kinetic energy function and the potential energy function. That's essentially, it's the sum of the two energies. And I'm going to explain what those mean in a little bit. But if you know what kinetic and potential energy are, you kind of get a basic understanding of what those actually would be. So potential energy function just kind of stays. The kinetic energy function is what we're actually going to break up into what it is. So this is going to, so we have the rest of this over here. We have the dt, and then same thing, psi x of t. And then this is going to break up, and it's going to become squared. It's negative, actually. Reduce Planck constant squared, 2 times the mass. And then we have nabla squared, which I'll explain what nabla is in a second. And then psi x of t plus, then we have potential energy function, Vx of t, and also psi x of t there because it distributed, and they multiply by each other. So nabla, this upside down triangle, is essentially just a stand-in for the derivative. Nabla squared is just double derivative, essentially. Nabla is regular derivative, nabla squared is double derivative. It's pretty self-explanatory. And then we have like, this is just regular derivative over here. I don't know why it's like that. That's just kind of how it is. So yeah. All right, well, first thing I want to deal with is potential energy function here. Now, the particle that we're dealing with in this place only has kinetic energy because we're going to be dealing with, say, a particle moving in a straight line with no external forces interacting with it. So because of that, it's not going to have any potential energy. So if there's no potential energy, this just equals 0. So the whole part of that just cancels out and goes away. And we just end up I reduce Planck constant, d dt, psi x of t, then all of that. And it's just going to equal the kinetic energy function, nabla squared, psi x of t. So what we're going to do now is we're actually going to find the double derivative of the wave function. So the wave function, here I'll use red pen for deriving. We'll go on to a different page over here. I'll flip it over, and then we'll come back to that. Also, I would like to mention on my last video, the Chris Chan vid, I got my first hater, which is kind of like a milestone almost. It's kind of cool. So we're going to write down psi x of t. This is actually, if you watched Oppenheimer, this is the thing that they write down in it, which I guess that's kind of cool, but like, it should mean anything. A, E, and it's going to be the power of I kx minus omega t. And that's the wave function, essentially. And we're going to find the double derivative of this. So first derivative, we're just going to do it by the rules of E. So we'll have psi prime x of t. It's become A. So the I is going to distribute, and it's become ikx, and minus omega t. In this case, we're deriving in terms of x for this. Yeah, what do you want? Never mind. Deriving in terms of, yeah, I can't keep this thing up. I was originally going to do it on my computer, but like it just straight up wouldn't let me log into my account. And I just kind of got fucked over by that. Which I guess is kind of stupid, but like, this is what it is, you know? Alright, where's that? Oh yeah. I comes down, I is going to be with the k of x, the x can go with the derivative, this is the constant, so it's gone. So the first derivative is just going to be literally ik, and then you have the rest of the e, because it's e, so it stays omega t. Then double derivative is just going to be xt, and this whole thing comes around again, it's just become ik again. So I squared becomes -1, so it's negative a k squared, boom, it's all to the kx minus omega t, and that's just the original function. So in other words, psi double prime x of t is just going to equal negative k squared, the initial function psi x of t, and that's the double derivative of it. Now if we go back actually to here, there's another derivative we need to do, which is just the first derivative, but this one is in respect to t, actually, in respect to time. So I'll show how that happens. So we'll do this one in, let's say green, because green's a cool color. So now we're finding, so we have the same function, psi x of t, and that's going to equal the same thing, ae to the I kx minus omega t. Just separate those two. But instead of us solving for, or deriving in terms of x, we're going to be deriving in terms of t, which is d to respect of t. So in this term, when we bring down from the e, the I kx minus omega t, in this case, instead of the kx being the derivative, in this case, it's going to be the constant, and then the omega t is going to be the derivative. So the t goes away, and then you're just left with the negative omega I. So in other words, that first derivative, psi prime x of t, is going to equal a, which is the normalization constant, and you have I omega, and then just the initial function, because that's the rule with Euler's number e. And then you have the initial thing, which is the same thing, initial wave function is going to equal I omega times the initial wave function. And that is the first derivative with respect to t. So we have our double derivative with respect to x, and our first derivative with respect to t. So now, we're going to go back, and we're going to actually plug those in. So this is going to be IH like before, and where was I? Oh yeah, we have the I omega, which we derived, and then just the wave function. And that's going to equal negative h squared. Well, actually, it's not negative anymore, but I'll go into that in a second. And then we have negative k squared, which we derived psi x of t. And that's where we end up. So I'm going to talk about omega for a second. Omega is the angular frequency, which in this case is going to be E over the reduced Planck constant. And I'll actually do that later in a second where I show why that is, why it is. So we plug that in. There's also two i's here, so they square, they become -1. So we get negative reduced Planck constant, E reduced Planck constant, and then psi x of t is going to equal, then the negatives will cancel here, so it's going to become reduced Planck constant squared, 2m k squared, and then the wave function. So we have this. Now there's a h bar, they're going to cancel out. There's two wave functions. Those also cancel out and end up with energy equals h bar squared over 2m k squared. So now we're here. Now k is the angular wave number, and it's going to equal 2 pi over lambda. So it's going to square that. K squared is going to be that squared over lambda squared. I'm out of space in this page, so we'll just flip over a little bit. Past there. So now we'll just write down what we initially had. E equals, what I said? I'm losing track. H bar squared, 2m, k squared. And then k equals 2 pi over lambda. All right, so factor that in, we're going to get h bar squared along with the 2 pi squared, and on the bottom, 2m lambda squared. So this h bar squared, 2 pi squared. Now that h bar 2 pi, which is reduced Planck constant times 2 pi, is just going to equal the regular Planck constant. They're both squared. So in conclusion, energy equals, oh wait, that's not reduced. Just regular Planck constant squared over 2m lambda squared. And that's the final equation for the energy or the kinetic energy of a particle without mass using the Schrödinger equation. Now, another thing I wanted to do is I talked about omega, where I said the regular wave frequency, angular frequency is going to equal E over reduced Planck constant. And the reason that actually is kind of cool. So if you took energy, for example, and you said like energy of a particle without mass is going to be Planck constant, velocity over lambda. And velocity, which would be c, for example, if you're doing like a photon, hc over lambda, but in this case it'll just be regular velocity because we're dealing with a particle that is lambda, or I mean is a photon, isn't a photon, doesn't matter what it is. So you actually put that in. You actually put that in and end up omega equals hv over reduced Planck constant and then lambda. So we have reduced Planck constant and regular Planck constant. Now that regular Planck constant is going to equal, reduced Planck constant is going to equal 2 pi, reduced Planck constant equals regular Planck constant over 2 pi. So you put that in, angular is going to be h v 2 pi over h again, lambda, they switch places to do that. Planck constants cancel out, and you end up, angular frequency is going to be v 2 pi over lambda, and v over lambda equals frequency, and you end up with angular frequency equals 2 pi frequency, which is just the regular for like standard Newtonian physics, like you would learn in your regular physics class. And that's essentially the conversion between the two. And another thing I want to talk about is the difference between relativistic and non-relativistic equations. Like you have, for example, if I were to replace m here, like I wanted to find energy of a photon, hc over lambda, and I were to use like Einstein's E equals mc squared. Yeah. If I were to use like Einstein's E equals mc squared, for example, and I were to rearrange that so we get m, so m mass equals literally E over c squared. Yeah, go away. Equals E over c squared, and then I just plug that in. I would actually end up with an answer that's somewhat similar. So I'd get E equals, we have h squared c squared over 2e lambda squared. Then you multiply by e, and you essentially end up with e squared equals h squared c squared over 2 lambda squared. And if you just square root the entire thing, you're going to end up with e equals hc square root of 2 over lambda, which is very close to the initial, but is actually incorrect. And the reason it's incorrect is because this is relativistic when this is not. And you can't actually combine relativistic and non-relativistic equations. It's an example of that. You can see that the results are very similar, but there's that square root of 2 there, which sort of throws it off and kills the entire thing. And that also gets into like string theory, for example, where trying to link fields like quantum, relativistic, non-relativistic, and just classical physics in general and link them all into one united field. And I don't think that like we can feasibly do that. Like I think string theory is kind of stupid, and I know a good amount of people agree, but a lot of people also disagree. But that's literally just the look at it. Is string theory would just be trying to figure out how to get rid of that square root of 2 so that we can show a link between relativistic and non-relativistic, but it doesn't actually work like that. But I don't want to do too much more, but I'll probably do like one additional demonstration where I'll do something with like the normalization constant. I'm going to use red. So I'm going to show how to solve for the normalization constant. So essentially, when you're solving for the normalization constant, which is that a in the wave function, just sort of like the sum of the area of where the particle is, you're solving for the integral, limit to infinity, that's not an infinity sign, down limit to negative infinity, and then it's the integral of the absolute value of the probability function squared respect to x, and that all equals 1. So you take that, we have our wave function, which we know, ae to the I kx minus omega t, for example, and we sum those together. Now when you do this, whether this is positive or negative, this exponent here actually depends on the direction that the particle is going. So for example, if it's negative, it's going to the left. If it's positive, it's going to the right. This is assuming it's on a one-dimensional plane, which usually the particle wouldn't be, but like in physics, when you're representing that, it's just how it's put, just being a simpler term and to sum things down a little easier. So because we have an absolute value here, it actually becomes, when we integrate, we have that a becomes squared with the rest of it, and then we have e to the power of I kx minus omega t, and then you have the same thing, but it's negative on this side. because the absolute value bar. And anything to the power of something times that same thing to the power of the negative thing is always going to equal 1. So this all cancels out and becomes 1. And you're left with just the integral of the normalization constant squared d of x equals 1. And that is going to become a squared x plus constant c equals 1. Now, in physics, that constant c is literally just thrown out, so it just equals 0. We just sort of exempt it entirely from the thing. It's just not included. This is just because it would throw off the proportion, like throw off the offset of where the equation actually is, where the particle actually is. And it's just sort of not necessary. So in quantum physics, you get rid of the constant c, it's not necessary. So we have a squared x equals 1, divided by x, a squared equals 1 over x, and then you just square root the whole thing. And I'll use green for the answer. So the normalization constant equals 1 over the square root of x, where in most cases that x is going to equal the box, or the limit of the particle that it's in, and the normalization constant will usually just be 1 over the square root of L. And that's how you solve for normalization constant. I don't really know what else to talk about. It was a relatively short stream. I just kind of wanted to do this for one person. Shout out to Tyler, great guy, the person who wanted me to do it. Well, no, I wanted to do it, but he's the one who said he would like it. I wish I could have used Adobe Paint. That would have been better, but my computer's annoying, so we didn't end that. You got this instead, and I didn't know how to do a few extra things, I guess. So yeah.